Hi guys, I know we covered this in our live lesson, but before I go on, I want to make sure you're solid on it. So this, the idea of a semiconductor can be tricky to get your head around, so it's worth taking your time making sure you're solid on it. And the second half of this lesson, I'll go into the new stuff, specifically doping of semiconductors. So first off, what is a semiconductor? Well, it's a material that has a resistance somewhere in between that of a conductor and an insulator. But the really strange thing about semiconductors is, as you heat them, their resistance decreases. So that's in direct contrast to virtually everything else. With most stuff, as you heat it, the atoms that make up the material vibrate more, and that way any electricity passing through is more likely to hit those vibrating atoms, and it's more difficult for electricity to pass through material usually as you heat it up. But semiconductors are different. Now, to understand why semiconductors behave the way they do, first off, we're going to look at an example. That's the easiest way to do this. So most semiconductors are made of either germanium or silicon. Now they're both in group 4 of the periodic table. They both have 4 valence electrons. And I'll explain what that means in just a moment or two. So we're going to use silicon as an example. So a semiconductor is basically just a block of silicon. So here's just a block of silicon. Now obviously that block is made up of many, many billions of atoms of silicon. So I've done this to represent the little individual atoms of silicon. And the atoms arrange themselves into a kind of a crystal lattice, into this kind of shape. Now, this is a simplified version. I've tried to make this look two-dimensional. In reality, it's obviously in 3 dimensions, but this is as good as. So they're joined together by covalent bonds that join each of the silicon atoms in the crystal structure together. And each one, if you notice, is joined to 4 others. Okay, so let's get to why this structure arises. So first off, if you look in the periodic table, both carbon, silicon, germanium are all in the same group, the same kind of column of the periodic table. And they each have 4 electrons in their outer shell. So how would you know that? Okay, well, let's take silicon, for example. If you look at silicon, it has an atomic number of 14. Now what that means is that it has 14 protons in its nucleus. Now because the atom is neutral, however many protons it has in the nucleus, it has to have the same amount of electrons. So if it has 14 protons, it also has 14 electrons. And those electrons are organized into shells or orbitals. Now I'm slightly oversimplifying this just because we're not going into the chemistry of it, but they kind of go into individual kind of orbits, individual shells. So the first shell can take 2 electrons. They can fit into the first kind of orbital path. The second shell can take 8, a maximum of 8. And the third shell can take a maximum of 8. But we're only dealing with 14, so if you put 2 in the first, 8 in the second, that leaves us 4 for the outer ring of electrons. These are the valence electrons. Electrons that are free to do stuff. The ones that are in the kind of lower orbitals are kind of locked in there. They're not going to do much. But you are able to get the outer electrons to interact with other stuff. And in fact, the inner electrons are not really relevant to us. I'm just going to kind of ignore them for now. They're there, but they're not relevant to our understanding of how a semiconductor works. So let's just focus on the silicon nucleus and its 4 valence electrons, those 4 outer electrons that are free to interact with other things and free to, bond on covalently. Okay, so if you remember, those that shell wants to have 8 electrons in it. So for one silicon atom alone to fill that shell is not going to happen. Instead, it needs some friends. So if you get 4 other silicon atoms surrounding the original, then they're able to covalently bond with each other. Now what that means is they share a pair of electrons. So if you look here in this diagram, the central silicon atom there has now got 8 electrons in its outer shell. So it's kind of stable. And it's gotten 1 from each of its neighbors, 4 neighbors to each side. And this is just a very small part of a much larger crystal. So that silicon next door is also going to have a neighbor on the other side. So overall, each silicon atom in the crystal is bonded onto 4 other silicon atoms by covalent bonding. Okay, now that's what happens at 0 Kelvin, right? So the 0 Kelvin is when there's absolutely no heat, no vibrations, nothing's shaking, nothing's happening at all. So at 0 Kelvin, absolute zero, the semiconductor acts like an insulator. No charges are free to move around, they're just stuck kind of in situ. So there's no kind of conduction going on, it acts as an excellent insulator. But let's think what happens as we go above 0 Kelvin and as we approach, say, room temperature of 20 degrees Celsius, thereabouts. So at this stage, when you've got an increase in temperature, that's basically an increase in energy. So for these electrons now, they've got more energy available to them. And if you give an electron more energy, eventually it could escape from the covalent bond that it was a part of originally. And when it escapes, it can move and it's now suddenly free to carry a negative charge. But the story doesn't just end there, because wherever the electron left, it's going to leave a kind of a gap where it used to be, a positively charged, we call it a hole. It's like the absence of an electron. So wherever that electron was, you're now going to have a positive hole there instead. And here's the thing, that positive hole could be filled by another electron. Another electron might be attracted to that positive hole and go to it. But wherever that electron came from is then also going to leave a positive hole. So what this means is you can have negative electrons and positive holes moving around through the material, so you can conduct a charge. This movement of electrons and positive holes is known as intrinsic condition. And there's an equal number of positives and negatives just moving from place to place within the semiconductor. Okay, so let's look at a particular example of a semiconductor. So a thermistor is just like we talked about. As you heat it, its resistance is going to decrease. So it's a semiconductor whose resistance decreases rapidly as you increase the temperature. Its symbol is kind of like a normal resistor with that line through it. And it's usually used to control the temperature of stuff. So your oven's thermostat or central heating, anything where you want to control the temperature of something would probably have a semiconductor inside. A variation, a different type, is a light-dependent resistor. This time, it's not heat that causes the resistance to decrease, it's light. If you shine light on a light-dependent resistor, that light energy can give the electrons extra freedom to move. So as you hit it with more light, you get more electrons moving around, so again, you get that decrease in resistance. And you usually find these on things where you want to sense when something's dark or light. So, those little garden lights that charge up during the day and then turn on light automatically, they'll use a light-dependent resistor to control their circuit. They're also using security systems like burglar alarms and stuff. So we've established that with semiconductors, their resistance will decrease as you increase the temperature. So what if you want to make them better at conducting electricity? What if you want to get that resistance down even further? Well, you can do it through a process called doping. Now, if you think of doping in sport means that an athlete has taken drugs. So they've kind of introduced a chemical somewhere they shouldn't have. And in this sense, it's kind of similar. We're introducing a chemical impurities. Now, when I say impurities, you can't just chuck in a random scattering of anything. We're talking kind of precise, controlled substances here. I'm going to leave that in. That's an inadvertent joke, but I'm going to leave it in. So, in particular, let's look at two examples. Now, in this one, I've drawn phosphorus as a little square because my orange cardboard looks very similar to my red. So I've drawn it as a square to try and make it look distinct. So let's say that we introduce some phosphorus here and there amongst the crystal matrix of silicon. Now remember, there's billions of silicon atoms, but let's say we put in a few phosphoruses. The thing about phosphorus is it has 5 valence electrons, not 4 like silicon. Now it's roughly the same size as silicon, its nucleus, so it'll fit into the lattice quite well, but it also now comes with this extra electron. Now I want you to be clear here, it doesn't mean that you've suddenly given this thing a negative charge, right? We call it an N-type because you have more negative charge carriers now, you have more electrons to kind of roam around. But overall, the whole thing is still balanced. You still have the same amount of protons as you do electrons, so we're not giving this a charge here. It's still balanced, it's still neutral, but we now have more negative charge carriers available to carry a charge. So because we have more negative charge carriers available, we call this type of doping N-type doping. In contrast, we're going to look at positive type doping next. So in negative type doping, we introduced impurity with a valence of 5, so 1 extra electron. If we're trying to get a positive impurities in, we're going to use an element that has 1 less valence electron than silicon. So for example, if we introduce boron, which has 3 valence electrons, 3 electrons in its outer shell. Just like before with phosphorus, it's of a similar size to silicon, so it can fit neatly into the matrix, but it has 1 less valence electron, so you've introduced a positive hole. Now again, overall, the whole thing is balanced, same amount of electrons, same amount of protons, but now you've got more positive charge carriers available because you've got more of these holes in the structure, these positive holes. When we use doping to increase the conductivity of a semiconductor, whether we use P-type or N-type, we now refer to this as the extrinsic condition, that you're able to carry more charge because you've added some impurities that will have more charge carriers in them. A lot to take in on that one, guys. So make sure you're solid on it. And as always, don't hesitate to get in touch if any questions. It's not easy at all. Okay. Please don't hesitate to get in touch if you're wobbly on it. And I'll talk to you soon. Fair play.